Hello. Let's continue with the gas laws that we started last time. So we finished up to the combined gas laws. The next one is Dalton's law of partial pressure. So simply partial pressure, right? So what's the partial pressure? When you have a couple of gases, let's say in the same balloon, we filled air, nitrogen 78%, O2 20%, and CO2 0.04%, right? So roughly, so there are other gases, but these are the most prominent ones, important ones, right? So we can write it this way. That's the mixture in the balloon, and we can write PA is let's say PA is N2, PB is O2, and PC is CO2, right? And that's how we get the 1 atm for the air pressure surrounding us. That's also considered as P total. So that means P total is partial pressure of nitrogen, oxygen, and CO2. Okay, so CO2 is actually 0.04%. So let's correct that. Okay, so those are the partial pressures of the three gases that we are considering in a sample of air, right? So that's called the Dalton's law of partial pressure, right? So it's pretty simple. Each component together will give you the total pressure, right, for the sample. So now there's another important thing we should know. That's the mole fraction. What's the mole fraction? Actually, it's the mole fraction. So what's that? If you're considering moles of A is divided by total moles of the whole sample. In this case, actually, mole A should be divided by A plus B plus C, right? All the moles together. So that's called the mole fraction. It gives you an idea because it fills this balloon. Let's say we have 8 particles of nitrogen and 2 particles of oxygen, let's say. So that means we can write the partial pressure of nitrogen is actually mole fraction of nitrogen times the total pressure, P total. So mole fraction is written as XA or X nitrogen in this case. And so if I have, let's say, total of 8 moles of nitrogen and total 8 plus 2, 10, 8 divided by 10, P total, that's how you get the partial pressure of nitrogen and then oxygen and so on, right? So actually here, yes, for the oxygen it should be 2 divided by 10 because we thought there's 2 oxygen molecules and moles and 8 nitrogen moles, right? Okay, so that's the simplified version of Dalton's partial pressure law. Now, we also have to think about the kinetic molecular theory, we call the KMT, and that's simply think about just some imagined box that there's a particle, gas particle moving randomly, right? And then it go and hit the walls if it is a container, right? Let's say glass box, and it randomly hit every corner and bounces back, right? So these are certain speed, and then it's keep moving, right? So that's the kinetic molecular theory. There's a kinetics, right? So let's keep it this way. So there's an easy way you can think about that one. That's called the Raywood. So that's what's the ray? Random motion of particles in a sample. And A4 attractions are none. So there's no attraction between the particles. And volume, we consider almost no, actually minute or negligible volume of each particle itself. And the collisions are elastic, so that means there's no loss of energy in each collision. And also the duration we are considering in these motions are very little time, picoseconds, nanoseconds, and even smaller than that. So therefore, the Raywood will tell you what's the KMT, what's the kinetic molecular theory is. So we use the kinetic molecular theory to understand and explain behaviors of gases. So this all depends on the temperature, right? So temperature goes up, the kinetic energy goes up, more motion. faster movements of particles. Okay. Now we can also write the kinetic energy is half mv squared. You perhaps remember from your physics class in the high school. So v, the velocity of the gas, is actually root mean squared. So we can write that way too. And if Graham's effervescence law, and simply know diffusion. Diffusion is simply more concentrated gas molecules goes into low concentrated areas. And if someone is wearing a perfume and you can smell it across the room, that's because of the diffusion, right? But effusion is a little different. You need a vacuum tube and you fill, let's say, ammonia gas, and you punch a little hole, and then the ammonia gas escape into the vacuum. And that's faster because its vacuum does not force a thread. How do you know about this one? You need to have another gas, something like HCl. So hydrochloric gas, in the other side, you punch a hole and release into the vacuum. So what's going to happen? The molar masses of ammonia is 17 and HCl is about 36. And so the HCl is heavier and ammonia is lighter. What happens? Ammonia moves further and the heavier one moves less, right? So eventually we're going to see a white cloud in this area. That's ammonium chloride solid. That's how actually Graham's law came up with. That was the experiment. And you can write this one for mathematical problems. Rate 1 divided by rate 2 is molar mass 2 divided by molar mass 1, because it's the inverse proportionality. Because heavier the gas, slower the motion, or the rate is lower. That's what the idea, right? So not only some of the problems you can get, instead of the rate, you can say distance divided by time, right? That's a rate. And you can have distance x, distance y, then you can do the same calculation. So you will be using inverse proportionality on it. Okay, all right. So let's think about a few other things. So I have been using ideal gas, but we know ideal gases are not really existing, right? They are hypothetical. And ideal gases have 22.4 liters in 1 mole at standard temperature pressure. And real gases, really, we see it here. It's the nitrogen, oxygen, water vapor, CO2, methane, things like that. So they are real. They are actually existing here. So why are we talking about these two? Because the gas behavior is much better if the gas is smaller in size and it's a higher temperature, higher Kelvin value, and also lower pressure, and if you take a larger volume. So that means they behave better as a gas. You can imagine if you compress a gas, it's going to make a liquid, so you can't apply gas laws, right? So those are the two things you have to know. So all the gas rules are followed by ideal gases because it's hypothetical, right? Okay, so now this one, the Henry's law, that's a little bit different. This is mostly for the pre-meds and dental and students. I mean medicine, pre-meds and dental students mostly. So Henry's law is, if you have, imagine your pop scan, right? You have water and CO2. So the CO2 solubility is depending on the concentration, right? And then we have Henry's constant. So solubility of the gas times Henry's constant is depending on the pressure of the gas, right? So solubility depends on the pressure of the gas. Okay. Now, so we also use combined gas law, Charles and Gay-Lussac's law together. I think you remember last time we talked about that. So the combined gas law is these three gases laws together. T1 V1 over T1 can be written as P2 V2 over T2. So we can use that one for any situation, because if you have V1 the same, then you cancel it out, so you get the Gay-Lussac's law. if you have the, let's say, we can get, let's write P1 V1 T1, and then P1, the pressure is the same, so that means it's the Charles law, V1 over T1, V2 over T2, right? Now we also can combine with the Avogadro's law, then we can get the PV is nRT. That's also with the combined gas law and the Avogadro's law together, right? What's the important thing here? The number of moles are there, and then the R, the gas constant, 0.082, and it's actually LATM over K mole, right? 0.082 LATM over K mole, or for most of the PChem problems, physical chemistry problems, you will be using 8.3145 times units are joules over K mole. So this is also you use. Depending on the types of other units you have in the equation, you have to choose the right R. Okay. Now, so the last thing I wanted to talk about, the PV is nRT other applications. So we know number of moles are mass in grams divided by molar mass. We can plug in that here, replace N with the mass in grams and molar weight, molar mass, and you do the cross multiplication. You can write it this way, M over V. What's the M over V is actually density, right? Density of a gas, because it's given in grams per liter, right? Therefore, now we can plug in that here. So the molar weight is density of the gas, and the RT divided by P, right? So therefore, we can actually find out a molar mass of a gas easily. Okay. Now, what's the other one? The Van der Waals equation. This one, you don't need to memorize. Most of the time, this will be given if your professor is talking about that. So what's the difference? PV and RT still, but the Van der Waals equation explains real gases do take some volume of the container. So this missing volume should be here. That is the correction. And then the pressure is different because of the intermolecular forces that gases have. So that should be corrected with the other N squared A, right? So, okay, we'll work with some of the problems. Thank you.